I'm going to talk today about precipitation, how it happens, how we measure it, and then I want to get in a little bit to why it's so difficult to predict the weather. So why do we study precipitation? Well, we need water to live. Precipitation fills all of our rivers and reservoirs so we can pump that water to fields and grow food and have a supply of water for our homes. We also use precipitation or our water bodies quite a bit, for recreation. So I've included here this map. This is the area where I live in Colorado, and you can see all these blue lakes and reservoirs. Particularly, this is a big one, Horsetooth Reservoir here, another one down here, Carter Lake. Most of these lakes are man-made. Most of these lakes are just holding water so that when it gets dry, sometimes we have that extra water stored so we can use it to keep, ourselves hydrated and for everything we need water to do. Obviously, precipitation affects our daily lives as well. When it snowed last week, if we had all been in our schools, we would have been hoping for a snow day for sure. And also too much or too little precipitation can cause a lot of problems. So if you get too much precipitation, there's some flooding. So this is some flooding that happened near my parents' house that I just happened to be home that we saw a few years ago. Too little precipitation causes drought. So things will dry out, and then you'll hope that you have that water in storage that you'll be able to use when it doesn't rain for a very, very long period of time. So how do we get clouds and precipitation? And the recipe for clouds and precipitation is actually pretty simple. And there's a lot of vocabulary words on this slide, but I'll go through and I'll talk more in detail about them as we go through the next couple of slides, and hopefully everything will start to come together and make sense. So the recipe for clouds and precipitation, the ingredients, there's only 3 of them. It's moisture, rising motion, and something called a cloud condensation nucleus. And all you need to do is lift your air until it cools to the dew point and becomes saturated. Once the air is saturated, the water vapor condenses back into liquid water, and that happens on cloud condensation nuclei. And then you just have to grow your cloud droplets large enough so that they can't stay in the cloud anymore. They're too heavy and they fall out as rain. So let's dig into this a little bit and look at our ingredients one by one. So where do we get the moisture from? So we have something in atmospheric science called an air mass, and that's just a big, big bubble of air that comes from a specific place. So here's a map in North America of most of where our air masses typically come from. So you can see you have air masses that come from over the ocean. You have air masses that come from over the land. And these air masses can move around with the wind. So if the air mass, or if the wind moves an air mass from over the Pacific Ocean up over to the land, all of the moisture that evaporated over the ocean is now available over the land to fall as precipitation. So this moisture can come from anywhere, any of the oceans. It can also come from the Great Lakes as well. Anytime the air moves over a body of water, it evaporates some of that water. And the warmer air can evaporate more water than the colder air. So we often say that warm air can hold more water than cold air. So these tropical air masses coming from the warmer areas in the south, they're going to evaporate more moisture than these polar air masses coming from up like in the Gulf of Alaska. And so since the warmer air can hold more water than cold air, if you cool that warm air down to what we call the dew point temperature, it becomes saturated. So the dew point temperature is the temperature that you cool the air to where it can't hold any more water vapor, and then you have to condense the water vapor back out. So if you can think of the example, if you take a glass of ice water outside on a hot day and you leave it on your picnic table, and you come back and you see that the glass is covered in water droplets, what happens is your cold water in that glass has cooled the air around the glass so much that it's reached the dew point, and then you have to condense that water out. The air is saturated, it can't hold it anymore. So it condenses on the side of your glass. So that's where your moisture comes from. So why do we need rising motion? The rising motion is what causes the air to cool. So the ideal gas law, you may be familiar with that, basically says that pressure and temperature are related. So higher pressure, higher temperature, lower pressure, lower temperature. So when you go up in altitude, the pressure decreases, and that's because the atmosphere, even though you can't really feel it, the atmosphere has weights pressing down on us. We have the whole atmosphere pressing down on us. But if you go up to the top of a mountain, you only have half of the atmosphere pressing down on you, so you have less pressure there. So as you go up in the atmosphere, you naturally get the air to cool because the pressure decreases. And that's how we get the air to cool to the dew point. So here's an example here showing at the surface, you have a bubble of air at the surface where the temperature is 92 degrees and the dew point is 60. If you raise it up in the atmosphere and the pressure decreases, the temperature decreases as well until eventually you reach the dew point, here in this example at 6,000 feet, and your cloud can form. So how do we get the air to rise? Well, there's a bunch of different ways we can force the air to rise. Warm air is less dense than cold air, so warm air rises. So you may have seen on the television weather forecast, the weatherman talking about warm fronts and cold fronts. This goes back to those air masses. So if you have a warm air mass meeting up with a cold air mass, or a cold air mass pushing into a warm air mass, that's where you get your warm and cold fronts. So you're forcing the warm air up over the cold air bubble. That causes your air to rise and cool to the dew point, and then you can get your clouds. You can also make warm air just by the heat of the sun. So very, very warm days, you can get a bubble of air to rise just because the sun has heated that parcel of air more than the areas around it. You can also get the air to rise with a barrier. So something like a mountain, the air can't go through the mountains, obviously, so it has to go up and over the mountains. So you can almost see in this image here how this one cloud kind of follows the shape of the mountain range as the air is being forced up and over it. So cloud condensation nuclei is just like the water vapor condenses on the side of that glass, it needs something in the cloud to condense on as well. You can't just turn a water molecule from vapor into water or into liquid again. It needs something to form on. And so this can be almost anything, dust, sea salt, volcanic ash, smoke, or even other cloud droplets. So once you have a cloud droplet form on a cloud condensation nucleus, more water vapor can condense onto that already formed drop. And these particles are really, 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 really tiny, not something you would be able to see with the naked eye. So here, if you compare in size, here's your teeny, teeny, tiny condensation nucleus. And here's what a typical cloud droplet, and even this cloud droplet you wouldn't be able to see with your naked eye. They're very, very small. A larger cloud droplet, you can see that. You'll be able to see that with the naked eye, but it's still very, very much smaller. This is just the top of what a typical raindrop would be. So your typical raindrop is much, much larger than your typical cloud drop. So once you start you've got your air to rise, it's cooled to the dew point, you've found some dust particles in the atmosphere and the water is condensing on those particles. All you need to get precipitation is for that to continue to grow as more water vapor condenses. And so they grow larger in a couple of different ways. First, as I mentioned, cloud drops can act as condensation nuclei. So more water vapor condenses on an already formed drop. We call that deposition. The drops can also crash into each other and break into multiple drops. And then they combine, so they'll either break into a bunch of smaller drops, or they'll combine into one big drop. And we call that process collision and coalescence. And eventually the drops get too big and they can't stay in the cloud anymore and they fall out as rain. And I've talked a lot about the cloud drops, and I wanted to take a minute to talk about raindrops because I really wanted to dispel the myth that raindrops look like the teardrop shape that you see here. That's not what raindrops really look like. When raindrops are small, they're almost a sphere. They're almost a circle, like a ball. But as they start to fall through the atmosphere, the air pushes up on the bottom of them. So the bottom of the raindrop gets flat, like in this 2 millimeter raindrop here. And the more that the air pushes up on the bottom of it, as it gets bigger, it actually gets kind of like this lima bean shape to it. And as it gets bigger and bigger, eventually it breaks apart into two smaller drops and the process can start again. So there's lots of drops in these clouds bumping around and hitting each other and breaking and combining until they eventually fall out as rain. So how do we measure this precipitation? Because we want to know how much we're getting so we can plan how much we want to store, how much we want to release, how much we want to send to the farmers. So the most accurate way to measure precipitation is with a rain gauge. So here's an example right here of a CoCoRaHS rain gauge. This is a program that I think it's in the resources that they're going to give out, that you could actually join CoCoRaHS and measure precipitation in your own backyard. So it's just a cylinder with a funnel on the top. The rain falls in, it goes into the cylinder. And you can see there's little lines on the cylinder here that tells you how many inches of rain has fallen. So this requires someone to actually go out and look at it. And of course, we live in a very big world and we can't have someone looking at rain gauges everywhere all the time. So we have automatic rain gauges as well. This is a tipping bucket rain gauge. So this is the cylinder here and it sits on top of that platform. And this right here is a bucket. There's two of them. It's like a teeter-totter. They go back and forth. And they tip back and forth when they fill with a certain amount of rain. So we know how much water that this little bucket can hold. When it teeter-totters over, it hits this sensor and it counts how many times it hits the sensors on either side of the teeter-totter. And that's how we figure out how much rain has fallen into the tipping bucket rain gauge. Now, I haven't talked much about snow, but if we want to measure snow, we do that, of course. Old-fashioned ruler, just stick it in the snow pile, see how much snow there is. But again, we're not everywhere, especially up in the mountains where a lot of snow falls. So this right here is what's called a snow tell site. And a snow tell site is a place where we can measure snow without ever having to be there. And it has this really neat thing, lost my mouse, there it is, called a snow pillow. So this right here is a big plastic bag full of liquid. And when the snow falls on it, the weight of the snow pushes down on that big plastic bag. And the liquid inside goes through some tubes and into a container inside this building. And we know how much water weighs, so we know how much weight is on the snow pillow by how much liquid is inside the container in the building. And that's all automated and sent back via this antenna to our National Weather Service and the places that use these observations. Another way we can measure precipitation is, of course, with radars and satellites. And in the next few slides, I'll talk a little bit about how those work on a pretty basic level. And another thing that is, I've never used it, but I think they're really neat. This thing right here that this gentleman is holding is called a hydrophone. And this is something that we can attach to a buoy in the ocean, and it sits underneath the surface of the water and it listens to the rain. And it listens and it can tell based on how loud the rain is, how fast it's falling, how big the drops are, how small the drops are. So that's just a really neat concept. I've never been able to use the data from one of those, but I think it's fascinating that we can just put something underwater and listen to the rain fall on the ocean and know how much rain is falling. So radar is something you've probably seen on TV, on the news. And this is kind of the best way we have to look at precipitation over a wide, large area where we don't have any of those rain gauges available. So the radar lives in this big dome. It sits up high above the ground so it can see over all the trees and buildings and things. And here in the United States, we have about 140 of them distributed all over the place, like you can see here in this map. And the way the radar works is that inside this dome is an antenna that spins around in a circle, and it sends out beams of radiation that go out and they hit the raindrops. And then the radiation energy bounces off the raindrops and it comes back to the antenna. So given how much energy comes back to the antenna, that tells us how many raindrops are in the cloud and how big they are. And from there we can figure out how much it's raining. So you'd see an image kind of like this, where you take all the radars over all the United States and you can see, that there's a big area of rain across the Midwest. Where it's green, that's less energy. That means it's not raining as heavily. Where it's yellow and red, that means more energy has bounced back to the radar from the raindrops. So it's raining more heavily there. We also have a radar on one of our satellites now. So instead of looking straight through the cloud horizontally, like the radar on the ground does, it looks through the top of the cloud, looks down towards the surface, And so it can give us a really good view of what's happening inside the cloud, looking from the top down as well. So satellites measuring precipitation, it's kind of similar to the radar, except they don't send energy out. They just wait for the energy to come up. So if you think about maybe on a hot day, if you go out to the street and the street's a very dark color and it's very hot and you put your hand a few inches above the road, you can feel the heat coming off the road. And that heat's always coming off of things. It's always coming off the Earth's surface. It's always coming off the clouds. You just can't always feel it. But these satellites can sense it. The satellites have different channels, kind of like your TV or your radio, and each channel measures a different part of the atmosphere. So one of the channels will measure the heat coming off the surface of the Earth. One of the channels will measure the heat coming from the surface and going through the clouds. One will measure what's coming from the raindrops. One will measure what's coming from the snow. And so you can see in this example, here's 9 different channels. They're all looking at the same exact thing. They're looking at the same hurricane, but they all look different because they're all looking at different parts of the atmosphere. And when we combine that information from all of those different channels on the satellite, we can then do some calculations and figure out how much rain has fallen. So how do we forecast the weather? And this is kind of, why is the weatherman always wrong? Well, I talked a little bit about thinking about parcels of air lifting, and we can take the whole atmosphere and divide that into those parcels. So you can imagine dividing the atmosphere into a lot of little boxes, and every box we have to know what's happening in every single one of those boxes. So we need to know what the temperature is in the box, whether there's a cloud in there, what the wind speed is. And we have an idea of that based on the properties of all of the boxes. So we have different observation networks and sensors. So for example, the radars can tell us whether it's raining in one of those boxes. All the red dots here are a surface observation network. So that's going to tell us the temperature and the humidity and the wind speed at all of these little red dots. So we can fill in the boxes there. We also have weather balloons. So this would be a big helium balloon. You can see it's right next to a person. They're very, very big balloons, but they have a little sensor packet on them. And as we send them up through the atmosphere, the sensor packet radios back information again about the temperature, the pressure, and the humidity and the wind speed as the balloon goes up. So then we can fill in all these boxes and tell them what's going on in the atmosphere right now. And sometimes we have to guess. So for example, you can see here in Nevada, there's no red dots there. So we'll have to kind of guess, make an educated guess about what's going on in those boxes. But once we've filled all those boxes with information, we have what we call a forecast model, and we can move that air around with the wind or with rising or sinking motions. So the air can now move around from box to box. And we have really complicated equations to explain how this works. And I'll show them to you, but I'm not going to talk about them much because they're very big equations. But you can see that they have labels. So how the wind changes from box to box in both the north-south and east-west directions, how temperature, humidity, and pressure all change as you move the air around from box to box and up and down. So those really complex equations go into a big supercomputer like this one shown here. And we do all those calculations. And it's a lot of calculations. So a 1 degree latitude by 1 degree longitude box, that would mean there are 64,800 boxes over the whole globe. And that's only one level. Now the model we use to forecast here in the US usually is called the high resolution rapid refresh model. And that has boxes that are about 3 football fields on one side. So you can imagine 3 football fields as a square. And then there are 40 of those going up to the top of the atmosphere. So that means there's over 76 million boxes to do all those calculations in every time you want to produce a forecast. And that's just one forecast. So you move it ahead 1 hour and you do 76 million calculations. And you move ahead the next hour and do 76 million calculations. So it's a lot of work to do these forecasts. And what if our observations aren't quite right? What if we have the wrong wind speed in this box or the wrong temperature in this box? Well, as we move them, right, we'll say the wind here is too fast and the temperature here is too hot. As you move it from box to box, those start to combine. And so your forecast errors start out small, but they can actually get really big as you move through the forecast the longer and longer you go. And clouds and precipitation make this even harder. So clouds don't always take up the whole box. And as I mentioned, there's billions of droplets in these clouds, and we can't keep track of every single one of them. So sometimes we have to make some assumptions about whether the droplets in the cloud are a lot of small drops versus a small number of big drops. So we make a lot of assumptions, and we call these parameterizations. And these parameterizations also simulate how the clouds and precipitation behave in the box, but they also introduce a lot more uncertainty into our forecast. And so I just wanted to finish up here with showing how that actually works in real life. So these are some forecasts that were made last week. The forecasts were made on Wednesday morning. And on the top here is the forecast for temperature. And on the bottom is the forecast for precipitation, so how much snow they were expecting to get in my neighborhood last week on Thursday. And every one of these lines is a different model. So each one of these lines makes a little bit of a different assumption about what those clouds are doing, or it makes a little bit of a different assumption about how we estimate the temperature when we don't have a sensor in the box. So there's all just a little bit of differences between each one of these different colored lines. And you can see that when they start the forecast, that they're all pretty much in agreement about what the temperature is on Wednesday morning. But as you go through the forecast, this goes into about late Saturday night. It's about 7 o'clock Saturday is when this ends. And you can see by that point that now we have one model that says the temperature is 38 degrees and one model that says the temperature is 55, and a bunch of different models in between. So there's a much larger area of uncertainty in there as you go farther and farther out, and all of those errors compound every day. And because precipitation is much harder and we have a lot more assumptions to make about it, you can see here that, at the beginning, they agree, and then this purple model starts the precipitation a lot earlier than, say, these orange models. This green model doesn't start until much, much later. And they just continue to spread out over time. And at the end of the forecast, we see that one model thinks we weren't going to get any snow, and this model thought we were going to get about 18 inches. So when somebody tells you that they have a forecast 10 days away and that they know what's going to happen in 10 days, you should definitely take that with a grain of salt, because there's a lot of ways for errors to get introduced and things to become more and more uncertain. So I'll stop there.